So Max Planck, very important figure in physics and chemistry. While studying characteristics of blackbody radiation, he comes up with a hypothesis about how matter gains and loses energy. And this is very different than any previous thinking on the topic of gaining or losing energy. What Planck says is that matter has the ability to gain or lose energy only in specific increments. And those increments are all multiples of some minimum increment of energy. And Max Planck gives a special name to that minimum increment. He calls it a quantum of energy. So here's our first new vocab word here, quantum. Probably haven't heard this one before. The plural of that would be quanta. So a quantum is defined as the minimum amount of energy that can be gained or lost by a particular atom. And this would be different for different atoms. Depends on the atomic structure or the electronic structure more specifically. But for any atom, this basic hypothesis is true, that the atom can only gain or lose energy in whole number multiples, integer multiples of the quantum. So how do we calculate this value that is the quantum? Well, lots of experiments have shown that a quantum of energy, we're going to use E for energy here, is proportional to frequency, the frequency of radiation that is either being absorbed or emitted, depending on whether we're gaining or losing energy. It's proportional to that frequency times a constant called Planck's constant. And we're going to use a lowercase letter h for Planck's constant. And then frequency is still the lowercase Greek letter nu. So we say that a quantum of energy for a particular atom is equal to E, or rather, we should say that energy is equal to E equals h nu. So Planck's constant times the frequency that represents the minimum energy can be gained or lost by an atom. Now, through experimentation, we've shown that Planck's constant is equivalent to 6.626 times 10 to the negative 34th. And it has units of joules times seconds. Now, first off, you'll notice that that's an incredibly small number. Very, very, very small value. Secondly, you'll notice the units joules times seconds. This is set up so that when we plug Planck's constant into the relationship E equals h nu, the seconds cancel out. Remember that frequency is measured in seconds to the negative first, or 1 over seconds. So if we multiply joules times seconds and seconds to the negative first, which is the same thing as 1 over seconds, the seconds cancel, and we get joules. And the joule is the SI unit of measurement of energy. Now, the joule itself is a derived unit. It's equivalent to a kilogram times meters squared per second squared. So just in case you're wondering what the dimension of energy is, it's mass times length squared per time squared. This isn't something that you really have to understand at a conceptual level, but it will be useful as we're doing calculations in terms of dimensional analysis. So something to keep in mind. A joule is equivalent to a kilogram times meters squared per second squared. But back to Planck. So Max Planck's proposal is that matter can only gain or lose energy in whole number multiples of a specific minimum amount that we call a quantum. So if you have multiple increments, let's say we have 2 increments of this minimum amount, we would call it, as a plural, quanta. We have 2 quanta of energy. Now, there's not a lot of tangible information here. There's not a lot of observable evidence with this discussion of the quantum and Max Planck. So to help us understand how this idea of the quantum and quantized energy is not consistent with wave theory, we're going to look at another example. This is actually an experiment, and this one was run by Einstein, or at least Einstein did a lot of work with this particular observation of the photoelectric effect. So that's what we're going to be looking at here next, what we call the photoelectric effect. So before we get into the chemistry here, let me just talk a little bit about what the photoelectric effect is. So we've got a diagram of a fairly simplistic experimental setup here where we have these metal plates. So here's a metal plate, here's a metal plate. One of these metal plates is going to have the ability to emit electrons. The other is going to have the ability to collect electrons. So we call this plate on the left here the emitter plate. The plate on the right is the collector plate. What we find is when we shine electromagnetic radiation onto the emitter plate, electrons can be ejected from the surface. So electrons will pop off of the surface of the emitter plate, and then they'll be directed toward the collector plate here. Don't worry too much about the battery here. This would just be if we were trying to look at this from a physics perspective and determine Planck's constant. You can apply an opposing electric field and actually stop the electrons from moving from left to right. And then based on the applied voltage, we can get that value for Planck's constant. If we plot the appropriate information, energy versus frequency is what we're looking at. It gives us joules times seconds, 6.626 times 10 to the negative 34th. That's where that value for Planck's constant comes from, at least in part one experiment that verified it. What we're interested in here is the fact that this incident light, as it strikes this emitter plate, can eject electrons. So photons are a concept that come into play here. It's something that we haven't talked about before. This is going to be a big part of Einstein's proposal, is this idea of photons. So we'll come back and take a look at that in just a second. So how does the photoelectric effect demonstrate the particle characteristics of light? What we find with the photoelectric effect is that you have to have a minimum frequency of electromagnetic radiation in order to eject an electron from a specific metal. So, if we have a certain metal plate on the left here, you will only be able to eject electrons if the incident light has a frequency higher than some minimum value. We'll call that, I'm using the physics variable. We use nu for frequency here in chemistry, so we'll call that nu naught. This is a minimum frequency. Anything less than that minimum frequency of light will not eject an electron from the emitter plate. And this is inconsistent with wave theory. Wave theory predicts that any frequency of light will be able to eject an electron if the intensity is high enough. And that's not the case. What we find is you have to have a frequency higher than this minimum frequency in order to eject an electron. So there's some limitation to the wave theory in terms of explaining this photoelectric effect. Furthermore, wave theory would predict that more intense light would increase the energy of the ejected photons. So ejected electrons, sorry. So that would mean that if we brightened the light, turned up the intensity of the light, these ejected electrons would move at a higher speed. They would have more kinetic energy. But this doesn't happen. Instead, what happens, as we increase the frequency, as we increase the intensity of the incident light, we get more electrons ejected, but they all have the same kinetic energy. So what the result shows us is that the energy of the emitted electron depends on the frequency of the light and not its intensity, and that is not consistent with wave theory. Instead, we see that the photoelectric effect supports the particle theory of light. This is more consistent with what we would see from particles like atoms. And this is a really, really important observation, has lots of significant consequences in the field of chemistry and physics. So Einstein studies this photoelectric effect, and in order to explain the observations, he proposes this idea of the photon. So a photon is a particle of light, or can be thought of as a particle of light. And Einstein is going to use this photon model in order to support what we call the dual theory of light, or the dual nature of light. So let's get a better definition for photons here. Photons are particles of light that can also be thought of as bundles of energy. They each carry a specific amount of energy that is proportional to their frequency. So we see that Einstein's model of the photon is consistent with Planck's descriptions of the quantum. In fact, we can use the same basic relationship. We can say that the energy of a photon then is equal to Planck's constant times the frequency of that photon. And so what we've done now is shown that sometimes we cannot explain light's behavior with wave theory, with the wave model of light. Instead, we need to look at light and treat light as a particle, photons. But at the same time, photons and particles can explain a lot of light's other characteristics, like the ability to undergo interference. So we need both the wave model and the particle model to completely explain the behavior of light. And Einstein proposes then a dual nature of light, that light has both particle properties and wave properties at the same time. And this is a very, very important conclusion because it's going to allow us in the future to think of particles as having wave properties. If light, which we traditionally think of to be a wave, can have particle characteristics, why can't particles also have wave characteristics? So that's something that we want to think about for future lessons.